to our showcase. The project that we have the pleasure of presenting today is called TREEREG, or Detection-Based Registration. I'm Damian Wilson, and I'm joined by my project partner, Chen. The input data provided to this project consists of orthomosaic maps of tree orchids taken at different dates, each with an associated set of feature detections. These feature detections come in the form of bounding polygons over individual tree instances, as seen in the second image. The goal of this project is to use these tree instance detections in order to align one input orthomosaic map onto another one via an appropriate image registration technique. The source of the data for this project comes from Aerobotics, a company in the precision agricultural sector that provides trend analysis of orchids on an individual tree level over time using drone-based imagery. The basis of this agricultural trend analysis are orthomosaics. An orthomosaic is an aerial map of an orchid created from individual drone images being stitched together. The analysis of these agricultural trends over time uses multitemporal orthomosaics as inputs, or orthomosaics at different dates. In order for successful trend analysis to occur, these input orthomosaics need to be correctly aligned. Image registration is the process of aligning these overlapping images of the same scene. Each orthomosaic comes with an associated set of feature detections. These have been produced by Aerobotics' tree instance segmentation model with the aim of using these in order as the basis of an automatic image registration process, as currently these orthomosaics are registered using a human-in-the-loop or human-based approach. The input data provided to this project can be summarized on the slide. Data pertaining to 3 orchids have been provided, each with Me and my partner have both used point cloud registration methods as proposed solutions to this automatic registration process. Point cloud registration involves registering one point cloud onto another one via an appropriate transformation. My specific point cloud registration methods that I implemented are called Iterative Closest Point and Coherent Point Drift. Iterative Closest Point involves the estimation of rigid transformation parameters in order to register point sets in iterations. It uses the hard correspondence of closest points between the 2 point clouds. It aims to minimize the distance between these closest point pairs with a least squares optimization. This approach is very simple and intuitive, however, it is very sensitive to noise, outliers, it cannot handle rigid deformations, and it falls into local minima traps, preventing an accurate registration. Therefore, in order to counteract these cons of the ICP method, I've implemented Coherent Point Drift. Coherent Point Drift is a probabilistic approach to point set registration, in which the source point clouds are modeled as centroids of a Gaussian mixture model and the reference point clouds as observations of that GMM. Transformation parameters are estimated to maximize the posterior probability that the reference point clouds are accurate observations of the GMM of the source point clouds, therefore providing an accurate alignment of the 2 point clouds. It does this via an appropriate expectation maximization algorithm. Due to its probabilistic nature, it can handle affine and non-rigid deformations too, unlike ICP, and is not as sensitive to noise and outliers. Hi, I will now be doing a live code demo on the Iterative Closest Point and Coherent Point Drift methods. First, ICP on the first orchid dataset. As you can see, the initial data provided to this problem consists of a reference cloud and a source cloud. The reference cloud are the centroids of the feature detections at the earlier date, and the source cloud is the centroids of the feature detections at the later date. As you can see, the data has already been pre-registered by Aerobotics' current human-based method. Therefore, in order to evaluate the accuracy of our methods, we'll first have to misregister the datasets and then apply our methods to the datasets and then compare the accuracy results of our methods to the current human method. Now the data has been misregistered. We'll now apply ICP to the misregistered data. As you can see, ICP produced a somewhat accurate registration, not as accurate as the human-based method. As you can see, the mean squared error of the ICP method is around 6.38. This is higher than the base mean squared error of the human-based method of around 5.04. A higher mean squared error means a less accurate registration. Therefore, ICP is not as accurate as the human-based method on this case. Let's see if CPD can do any better on this dataset. CPD will now be applied to the same exact dataset. And as you can see, it produces a much more accurate registration with a mean squared error lower than that of the human-based method. Let's test this again on another data set. We'll do this on the third orchid. As you can see, the data has already been initially pre-registered. We'll now misregister the data set and now apply ICP to this. As you can see, ICP has failed to produce an accurate registration due to it falling into a local minima trap. We'll now see if CPD can produce an accurate registration on this data set. As you can see, CPD is converging towards an accurate registration with each iteration, and it seems like it will eventually reach an optimal alignment of the 2 point clouds, and it has, in about 87 iterations, it produced a very accurate illustration with an MSC lower than that of the human-based method. Again, on all cases, CPD beats the human-based method, whereas ICP fails to match it. We'll now provide a robustness test against the addition of outliers on this data set. This is just one of the many robustness tests we have done on this data set. In this project, as you can see, additional noise and outliers have been added to the third ORCID. We'll now apply ICP to it, and again, ICP has failed to produce an accurate illustration as seen here. We'll now see if CPD is capable of producing an accurate illustration despite the addition of additional noise and outliers. And you can see CPD seems to be converging towards an optimal solution despite the vast amount of outliers that have been added to the dataset. For every one observation in the source dataset, an additional outlier has been added. Therefore, this model is an extreme case of outliers in the dataset in order to test the limits of each algorithm. Again, this outlier test is just one of the many robustness tests we have done in this project. This is just the most important one, and therefore the one that we will show in the showcase or in this code demo. As you can see, it's somewhat slower in order to reach an optimal alignment, but CPD does manage to accurately register the datasets visually. And again, it produces a lower MSE than that of the human method. Therefore, CPD is successful in producing an accurate registration, whereas
This is the robust point matching part of the project. Robust point matching is an iterative and probabilistic approach. It uses the technique of soft assignment and deterministic annealing. It estimates transformation parameters and correspondence at the same time. As shown by the diagram at the right, it has a control parameter which controls the progress of the algorithm. Inside the control loop, there are mainly two parts. The first part uses a cost function and soft assignment to estimate the correspondence between two orchards. The second part uses coordinate descent to estimate the transformation parameters between two orchards. And in this iterative fashion, the robust point matching can register two orchards. This is the demonstration of robust point matching algorithm. This shows the pre-register data. This shows the data after deregistration. The goal here is to register blue dataset onto the black dataset. This screen shows the robust point matching registration results. As shown, the blue dataset has been registered onto the black dataset. And this shows the accuracy registration test on orchard 2. The left-hand side is previous data, in the middle is the misregistered data, and on the right-hand side it is the robust point matching registered data. Same as the previous slide, this is the accuracy registration for orchard 3. In order to test the robustness of the algorithm, a low confidence removal mechanism has been applied, where points with low confidence level will be removed, and which results in more outliers. At the left-hand side is the previous data with a confidence level removal. In the middle it is the misregistered data, and at the right-hand side it is the robust point matching registered data. Same as the previous slide, this is the robustness test for orchard 2. And this is the robustness test for orchard 3. This slide shows the MSE and time comparison between human method and our methods. As shown here, ICP has a generally worse accuracy than a human method. CPD has a generally better accuracy than a human method. And RPM for Orchard 1 and Orchard 3, RPM has worse accuracy than the human method, but for Orchard 2, RPM has better accuracy than the human method. For the time efficiency, both ICP and CPD are quite efficient, but for RPM can be quite time consuming. And that would be all. Thank you very much.